Okay, welcome. In what follows, we are going to continue with Chapter 2, Architecture and Classification of Database Management Systems. So the purpose of this chapter is to zoom into the internal anatomy of a DBMS. And once we did that, we're also going to consider different types of classifications of database management systems. Here you can see the overview of the chapter. So concerning the internal anatomy or architecture of the DBMS, we're going to talk about a DDL compiler, data definition language that stands for. We're going to talk about a DML compiler, that's data manipulation language. We're going to talk about the query optimizer, which is a very important part of a DBMS. We're going to talk about the stored data manager, and then we're going to discuss different types of database system utilities. Regarding classification, we're going to provide different types of classification. So we're going to classify DBMSs based upon the data model. We already briefly referred to that in the previous chapter. We're also going to classify DBMSs based upon simultaneous access, system architecture, and based upon usage. And in terms of usage, we're going to talk about using databases for transactional usage. We're going to talk about using databases for usage in terms of strategic and tactical decision making. So let's start with the internal architecture or anatomy of a DBMS. Well, a DBMS has different components, being the DDL compiler, that's data definition language, DML compiler, remember, data manipulation language, the query optimizer, the stored data manager, and then various database system utilities. I'm going to start by discussing the general overview and picture of a DBMS architecture. So here you can see the different components and how they work. So we have DDL statements, data definition language statements. So that means that those will be statements which are going to create data structures, which are going to create the conceptual, physical, and external database model, for example. So a user, more specifically, a data modeler, is going to define all these concepts and then give them to a DDL compiler. The DDL compiler is going to compile all these data definitions, give it to the stored data manager, and the stored data manager is then going to store those definitions in the catalog. Remember, the catalog is the heart of the DBMS, and it contains all the metadata information. So it contains the data definitions, the data constraints, the data structures, and so on. Next to the DDL compiler, we also have various types of database system utilities, as you can see next to that. These will be performing all kinds of database-related utilities. That could be sorting data, that could be facilities for transaction management, that could be facilities for loading data, that could be facilities for performance monitoring, and so on. Then we have the DML part. DML stands for data manipulation language. And the DML compiler can be invoked in two different ways. It can be invoked directly by applications. So these could be Java applications, Java programs, or any type of other application, .NET applications, and so on. Could also be invoked by means of special statements. Think about interactive queries, for example. So somebody logs on to a front-end tool, is going to issue an interactive query there, and you want that query to be solved. So the DML compiler, together with the query optimizer, can be invoked in various ways. DML stands for data manipulation, and the data manipulation can come in various ways. It could be inserting new data, it could be updating data, it could be removing or deleting data, or it could also be finding data, querying data. In case it's querying data, we will need to make use of the query optimizer. And the query optimizer is a part of your database system which is going to optimize your query. So it's going to decide what's the best way to navigate to the source data in order to answer your query as fast as possible. All these components will interact with the stored data manager. The stored data manager, who's basically an interface to the operating system and will help you in retrieving the stored data. And that could be various types of data. That could just be the raw data, the database data, but it could also be the metadata, the data which is stored in the catalog. So here we're talking about data definitions, data constraints, and all kinds of data structures which have been defined during the database design step. Let's zoom into each of these components into a little bit more detail. The DDL compiler. So DDL stands for data definition language. So it's going to define the structure of the database. So it's going to contain all the data definitions. And ideally, we want to have 3 different types of DDL, which nicely cover the 3 different levels in the database architecture. So we want to have DDL instructions which are situated at the physical scheme level. Those DDL constructions will allow us to define how the data needs to be physically organized. Next to that, we also want DDL instructions at the conceptual scheme, which will allow us to define the various concepts, the data structures, the constraints, the integrity rules that exist at the conceptual level. Of course, we also want DDL at the external view level. So here we're going to define the views, right? Remember, a view is a subset of the data elements contained in the conceptual level, which are offered for a particular user or a particular application. So ideally, we want to have DDL instructions which are going to nicely cover those 3 levels of the database model architecture. However, in real life, it will often boil down to just having one set of DDL or one DDL language with different sets of instructions. Think about SQL. SQL is an example of a language which we will discuss later on, and which will just have one DDL with different sets of instructions to define the physical, conceptual, and external schemes. How does a DDL compiler work then? Well, the DDL compiler is going to first look at the DDL definitions that have been submitted to it. It's going to translate the DDL definitions. It's going to check the syntax to see whether there are any syntactical issues with it. If there would be syntactical issues with the DDL instructions, it's going to generate errors. And once there are no errors, once the DDL instructions can be successfully compiled, it's going to register the data definitions in the catalog, the heart of the DBMS. That's how it's going to work. Next component is the DML compiler, and there we need to make a difference between different types of DML operations. Remember, DML stands for data manipulation language, and we can have different types of data manipulation. We can have inserts, we can have updates, we can have deletes, or we can have simple querying. Querying means that you're gonna ask for information like, give me all the students registered for a particular course, or give me the average mark that students obtained for my course. So you have select or query of the data, you have insert, update, delete. These are all very commonly used DML instructions. And how the DML compiler is then going to work is as follows. The first thing it's going to do is it's going to translate the DML statement, the query, the update, the insert, or the delete. As with the DDL compiler, it will then check the syntax and see whether there are any syntactical issues with any of the statements that have been submitted. It will verify the DML statement using the catalog. So if certain pieces of information or concepts are being referred to, it will verify whether those concepts exist, yes or no. If needed, it will generate again errors. If there would be syntactical issues, it will generate errors. And once there are no errors left, it will perform the operation. It will update, it will delete, it will insert the information, or actually retrieve the information if it would be a query. If desired, the results of the DML operation can then also be presented to the end user. Now, particular focus can now be put on the query optimizer, because the query optimizer is going to collaborate with the DML compiler in case the DML statements concern queries. So a query, remember, is a question that you wish to address to the database. Question like, give me the students registered for this class, or give me the average mark that students obtained for this class. The query optimizer is going to process the query before it accesses the raw data, because it's going to find out what is the best way to access the data in order to perform the query as quickly as possible, in order to execute the query as quickly as possible. Because basically, as an end user, what you want is you want to issue the query and you want to have the results as quickly as possible. A query optimizer is a key part of a DBMS, but the thing is that it has not always been available in DBMSs. Definitely not in the early DBMSs, right? Later on, we're going to look at some of the DBMSs that have been developed in the 60s, in the 70s. Well, what was a key characteristic of those DBMSs is that there was no query optimizer available. Users had to write their own queries. They had to implement their own queries. This is no longer the case here. Here we have a query optimizer, and the query optimizer will optimize the query and it will find what is the best way to solve that query. So how is it going to work if you have a DML compiler and it needs to work out a query? So it's going to translate the query just as previously, and it's going to check the syntax. It's going to look at whether all the information elements, all the data elements that are being referred to in the query are known in the catalog, right? And see whether there are some syntactical issues there. And if there would be syntactical issues, it's going to generate errors. And it's going to say, hey, you're referring to a piece of information that I don't know, okay? Now, assuming that the query is error-free, it will then optimize the query. And when optimizing the query, as I said before, basically what it will do is it will find the fastest access path to the data. It will see how it can find the data in the quickest way, right? Such that the user has a very quick reply to his or her query. Then it will update, retrieve the data, and of course, if it's a query, the user is always interested in knowing the results of the query, and the results will be presented to the user in the end. The query optimizer is going to optimize the query, as I said before. It's going to find the best access path to the data. But in order to do so, it needs to intensively make use of the catalog. The catalog contains the metadata, the data definitions, remember. So the catalog is going to contain all kinds of data statistics, like what is the average number of students, or what is the total number of students registered, what is the total number of professors registered, what is the total number of courses. Maybe it's also going to keep track of some aggregated statistics, like what's the average number of students registered for a course, etc. Next to that, next to those data statistics, the query optimizer or the catalog also has all kinds of indices. And indices are fast access paths. It's like typically is represented as a tree-based structure which allows you to have fast access to certain pieces of information. It's part of the physical model. It's part of the internal scheme as we referred to it in the previous chapter. So using those two pieces of information, the indices and the data statistics, the query optimizer is going to determine the access path. It's going to work out a physical access path to solve the query. It's going to see whether it can use indices to access the data in a faster way. It's also going to throw away as many attributes as early as possible. Imagine that you have a student concept with many attributes. You have student number, student name, you have gender, date of birth, email address, and so on. And it turns out that the query is only interested in student number and student name. Then what the query optimizer will do is it will try and throw away all of the other information during query processing. So it will not look at student gender, it will not look at student email, not look at student birthday or student address, because it doesn't need that. So it will throw away that information as early as possible during query processing. The only reason why it does that is to basically speed up the optimization of the query, to speed up the actually answering time of the query such that the user can get the results in a fast way. Let's zoom into types of DML then, and basically you have two types of DML. You can have declarative DML and procedural DML. In declarative DML, data manipulation language, the DML statements specify what should be retrieved or what changes should be made. So the focus is on the what, not on the how. So the DBMS is going to receive that declarative DML statement, and then it's going to work out itself how it should solve that declarative DML statement. So it's going to determine the access path and the navigational strategy using a query optimizer, for example. So the DBMS will autonomously work out the declarative DML statement. The end user does not have to take care of it, him or herself. The end user only has to specify what is needed, and the DBMS will answer that question for you. This is often what we refer to as a set at a time DML. A set is a collection of information items. That could be a collection of students, could be a collection of courses, could be a collection of buildings, for example. And in declarative DML, typically you're going to work with sets of information items. It's set at a time DML, right? So it speaks for itself that declarative DML is a very powerful DML, since the user is only concerned with the what, not at the how. Later on, we're going to talk about SQL, for example, and SQL is declarative DML, because it just declares what is needed and not how we should solve the SQL query. In procedural DML, this is not the case. Procedural DML is a lot more inferior because we not only have to specify the what, but also the how. It speaks for itself that this is a legacy DML. That means DML that was used in the early approaches towards data management. So here the DML statements are going to specify how to navigate in the database, to locate and modify the data. So here, in other words, the end user has to program the query him or herself. They have to actually work out the different steps in accessing the data, how they're going to find the data, how they're going to iterate through the data, how they're going to summarize the data. All of that should be done by the end user, him or herself. So it speaks for itself that this is not very user-friendly, this is not very sophisticated. And usually the way procedural DML is going to work is that it's going to position on one particular record. Record is a piece of information. Think about one particular student. John Adam is a student. So procedural DML is going to position on one particular record, and from there onwards, it's going to step by step navigate through all the other records until it has found the information that it is looking for. So procedural DML stems from the fact that you have to work out a procedure, which is a small piece of programming code, to solve the query, be it an update, delete, insert, or just a simple select statement. The user is going to define any optimization if needed. So there's no query optimizer. In declarative DML, you will always have a query optimizer, and that will be a part of the DBMS that will optimize your query. Well, that we do not have in the procedural DML environment, because there the user has to optimize the query, him or herself. So that means that the user must know the details of the system, the details of the database system at a very low level, at a very physical level, to work out the query, and there's no query optimizer available. Remember, procedural DML is a record at a time DML. So that means that you position on one record, and from there onwards you navigate to the next one until your query is solved. So declarative DML focuses on the what, it's set at a time DML. Procedural DML focuses on the what and the how, and it's record at a time DML. Embedded DML is DML that is embedded in a particular environment, and that environment will often be an application. For example, in this course, you will do an assignment, and the assignment will mean that you're going to work on a real-life database. That means that you're going to develop a Java application. So the Java application will access a real-life database by means of embedded SQL or embedded DML statements in this case. You can have simple data interfaces for casual users. Think about Microsoft Access, where you have a forms-based interface to actually query data from an underlying data model, a forms-based interface. You have interactive query building tools in Microsoft Access as well. So these are very simple data and interfaces for the casual users. Of course, we will also have very powerful tools for power users. That means very big applications that are going to access a lot of data and are going to do very complex processing with that data. In any case, DML will be incorporated in the application environment, the Java environment, the .NET environment, and so on. And the application is often written in a host language. Java is the host language, so it's the language that hosts the data pre-processing or the data processing, right? The data access and the data manipulation. So that means that DML code will be directly embedded into the Java environment, and that's where the name the embedded DML is going to stem from. One particular example here is embedded SQL. Embedded SQL, here you can see an example of embedded SQL. So you have a Java program. We're not going to focus on the meaning of the program, so we're not going to run through every possible statement in the program. That is clearly of no interest here. So here you can see all kinds of statements in Java, statements that are going to make a connection to the database, statements that are going to read certain types of input from the command line, and at some point then you want to, in this particular case, find the name and particular age of a certain sailor. Here you then see an SQL statement, so he can see a delimiter. Okay, SQL stands for Structured Query Language, so it's the type of DML that is often being used by relational databases. And then here you can see the query, which is directly going to be issued to the underlying database, and then the database environment will give you an answer to that. So that's the data sublanguage here, right? So we have an embedded DML statement here, directly embedded in the Java host language environment. A key problem here is that we have an impedance mismatch. That means that the data structures of the DBMS and the data sublanguage may be different from the data structures of the host language. What do I mean with that? Well, remember the example I gave you earlier on. If you look here, this is a Java application. Java is object-oriented. It's going to work with objects that have state, behavior, that can have polymorphism, information hiding, where you can have inheritance, and so on. So Java is a purely object-oriented environment. But if you look at SQL, SQL is not object-oriented. So the data structures that you're going to use in SQL, and we're going to extensively comment on that later on, they're not object-oriented. They're relational data structures. So that means that you have a kind of mismatch, because on the one hand, you have object-oriented data structures in Java, in the host language, whereas the data structures of the DBMS and of the data sublanguage, SQL, they're not object-oriented, but they're based upon the relational model, as we will see later on. So both do not very well correspond to one another, so you have a kind of misalignment there. What is the solution? Well, there are different types of solutions if you want to work in this way. First of all, you can make sure that the DBMS and host language is in sync with the DBMS and data sublanguage is in sync with the host language, and that they use perfectly the same paradigms to represent data structures. A particular solution in this case is object-oriented DBMSs. You can use object-oriented DBMSs, which are going to store data as objects. And since Java also is object-oriented, then basically you have a transparent way of importing the data structures into Java, doing some manipulation, and then exporting them back to the object-oriented database environment. So that's a case in which you do not have an impedance mismatch. Another way of solving it is by using translation software. Translation software, which is going to translate the relational concepts to the object-oriented environment and vice versa. So this can be done using middleware, for example. Middleware is a piece of translation software that will allow you to map data structures from the DBMS to the host language and vice versa. It's translation software, very important. And later on in this class, we're going to see some examples of that. Here you can see impedance mismatch illustrated by an example. So remember, we have a Java class hierarchy here. So object orientation is a very important programming concept. So here we have a library item, we have a book, history, and transactions, and they're all related to one another using object-oriented concepts. This is then the MySQL representation thereof. MySQL is an open source relational database system. We're going to discuss it later on. So here you can see all the information concepts together with the information items. And basically the idea of impedance mismatch is that the Java objects do not map very well to the MySQL items. The data types will be different. The conceptual representation will be different. For example, in object orientation, you have behavior, which you do not have in a relational environment. So you will need translation software there. You will need middleware, which is going to map one to the other and vice versa. And as I said before, you can solve that problem either by using object-oriented database systems or by using middleware solutions that are going to translate the objects to a relational environment or vice versa. The stored data manager then is a next component of a database environment or a database application. It's going to control access to all data. And remember, the DBMS essentially manages two types of data. It manages the raw data, which is the application data, you know, the actual student, professor course data. Next to that, it also has the catalog, and the catalog has the metadata, the data about the data. It has data definitions, it has data structures, it has integrity rules, it has the definitions of the conceptual external and physical schemes. So it's going to control access to all these types of data and make sure that the data integrity is nicely guaranteed at every possible moment during working with the data. So that can range to from a simple interface to a full-fledged DBMS component. Simple interface to the underlying operating system to a full-fledged DBMS component. Kind of depends upon the DBMS software you're working with. Next to that, stored data manager can also include transaction, buffer, recovery management, or communicate with other types of dedicated components. Finally, we have some examples of database utilities. We have a loading utility. Remember, when you start a database application, once you have defined the data structures, your database should be populated. So it should actually be loaded with all the data that is needed. And here we're going to have a loading utility, which is going to load the data in the database. We're going to have all kinds of conversion tools, which will typically be part of an ETL routine. ETL stands for extraction, transformation, and loading. That means that you're going to extract the data from any source. That source could be an old database system, could be Word documents, could be Excel files, could be anything. So you're going to extract it, you're going to transform the data, transform it to make it suitable for the database environment in which you are working. Imagine that you're, for example, working in a relational environment, and the transformation is going to make sure that all the data is represented in a relational way. And once you have transformed it, you're going to load it into your database. So ETL stands for extraction, transformation, and loading. It's conversion tools to convert from one format, Excel, Word, or maybe some old hierarchical formats, to your particular target environment, for example, a relational environment. Other database utilities could be backup and recovery utilities, if you would have some tape infrastructure, for example. Reorganization utilities, performance monitoring to look at the throughput of your database environment, to monitor response times of your queries, and also some user management utilities. The DBMS is going to provide all kinds of interfaces to its environment. It's going to provide web-based interfaces for web client or browsing. It's going to maybe also provide you with some standalone query language interfaces that will allow users to specify their queries and run their queries. It's also maybe going to include a forms-based interface, like Oracle Forms or Microsoft Access Forms. Microsoft Access also has some very sophisticated forms utilities available there. Maybe it's also going to give you some GUIs, some graphical user interfaces based upon point and click, drag and drop, some natural language interfaces. Natural language interface could be like, think about your mobile phone, for example. When you have a mobile phone, many of the mobile phones, including an Apple iPhone, have a natural language interface. So you can use your human language to kind of steer the activities of the phone. You can say, call girlfriend, and then actually, this is a query, call girlfriend, because first of all, the phone number of your girlfriend needs to be retrieved. Hopefully that's only one phone number, and then once that phone number has been retrieved, the query can be solved, and the girlfriend can be called. Also, we have some dedicated DBMS interfaces here. We have interfaces for the DBA. DBA is the database administrator, remember? So that's the guy or person who's going to continuously monitor and maintain the database. Not a very exciting job, if you ask me. But anyway, some people do like it. So the DBA is going to create user accounts. He's going to grant authorizations. Authorizations means that the DBA is going to grant who has read access, who has write access. The DBA is going to set up system parameters, any kind of system parameters that are needed at the physical level, for example, to physically organize the data. It's going to change physical schemes or conceptual or external schemes or any kind of physical access paths. Of course, DBMSs should also be accessible in a networked environment. So that means that DBMSs should also offer all kinds of network interfaces to successfully accomplish this. Here you can see some forms-based interfaces. This is an interface from Oracle 10G. It's a web-based interface. You can see MySQL, which is an open source software. We're going to work with MySQL later on in this class, and you also see an IBM DB2 version 9 GUI interface. Okay, so this finishes the first part of this chapter. So remember, in the first part of the chapter, we zoomed into the internal architecture, the internal anatomy of DBMS. And we discussed the key components, so DDL compiler, DML compiler, the query optimizer, various types of database system utilities, and we also discussed the stored data manager. In the next big part of this chapter, we're going to talk about the classification of some DBMSs. And we can classify DBMSs in various ways. We can classify them based upon the data model. We can classify them based upon simultaneous access, based upon system architecture, and based upon usage. We're going to start based upon data model. So remember, a data model is basically a conceptual model which is going to gather user requirements. A data model is something which is typically built in collaboration between two parties. So you have the data modeler, the database designer if you want, and you have the end user, the business user. Remember the example we gave in the previous chapter in which a data model needed to be constructed for a university setting. So in that data model, you're going to clearly specify all the items that you need. So you want information on students, you want information on professors, on courses and buildings, but you also want to specify the relationships between all those data elements, like a professor can teach courses, a course is taught by professors, a professor or a course is being taken by students, a student takes courses. All those relationships need to be carefully modeled, and that's what we're going to do using a data model. Now, the way the data model has been formalized has changed throughout history, and the first types of data models that originated were hierarchical data models. And hierarchical data models are going to specify the relationships between all those information items, professor, student, building, course, as small hierarchies. We're going to comment on that in the next chapter. In the next chapter, that will be one of the first models that we're going to zoom into. So a hierarchical DBMS is based upon the hierarchical data model. And it's clearly that this is not a very sophisticated model because everything needs to be specified as a hierarchy, which is not very nice. But it was one of the first DBMSs that basically was developed in the context of the Apollo project, which we'll see later on. Here, the DML data manipulation language is procedural. That means that we're going to have to program procedures to work out our insert, update, delete, and select queries. So we have to program it. We do not only have to specify what, but also how. And remember, procedural DML is record at a time. So basically, when working out our query, we're going to jump from one record to the other. That also means that the definitions of the conceptual and physical scheme will be intertwined, right? So that means that you have a very tight coupling there between your conceptual and your physical schemes. Network DBMSs were a next development. They're a little bit more sophisticated, and instead of imposing hierarchies on your data items, they will allow you to develop small network structures between your data items. They're often also referred to with a kind of ugly name called codicil DBMS. So codicil is a very important implementation of a network DBMS, and we're going to extensively comment on that in the next chapter. But again, its legacy, it's outdated. It was developed in the late 60s, so the DML is again procedural, again focusing on the what and the how and record at a time. So it's not very sophisticated because just as with the hierarchical model, the definitions of the conceptual and physical scheme are intertwined. They're not well separated from one another. A lot more advanced is a relational DBMS, whereby you're going to specify information elements, students, course, professor, building, as relations. It uses the relational data model, and that's one of the models that we're also going to extensively comment on later on. And it's usually based upon SQL, structured query language, and SQL is the query language in a relational environment. And it will have instructions that will allow you to do DDL, data definition language, or actually define your data structures, and DML, data manipulation. The DML is not procedural. Now that's very nice. The DML is declarative. It declares what you want. So any kind of relational DBMS will have its own query optimizer. You just issue the query to the query optimizer, and the query optimizer will basically optimize the query for you, which is very neat, which is very nice, which is very cool. So that means that the DML is set-oriented. You're going to work with sets of information items instead of record-oriented DBML, DML, which was the case in the hierarchical and the network DBMS. So there we have data independence. That means that that three-level architecture, conceptual scheme, external scheme, and physical scheme is that you have nice independence between those three levels. Finally, and we already referred to it briefly, we also have object-oriented DBMSs. Object-oriented DBMSs are based upon the object-oriented data model. So in the object-oriented data models, you have objects that have state and behavior. So the state describes the characteristics of the object. Right? So you can have a student with a particular state, like student number, name, date of birth, gender. These are the attributes that describe the student's behavior. But next to that, you also have the behavior itself, like a student can register for a course, a student can pass or fail a course. All of these are small pieces of code, small pieces of functionality, which actually come with the student object. The ODMG, the Object Database Management Group, is a kind of international consortium which is going to come up with all kinds of standardizations for object-oriented databases. And it has defined a standard object-oriented model with an object definition language, an object query language, and some language bindings. So language bindings are particular implementations of all these standards in a particular language environment. That language environment can be C++, Java, or Smalltalk, for example. Typically object-oriented environments there. The nice thing about the object-oriented DBMS is that you do not have an impedance mismatch. Remember, the impedance mismatch was a mismatch that you had when you're using one way of representing information items, object-oriented, and another way, like relational representation of information items. So there's like a gap in between that you have to bridge, and you can bridge that gap either by using an object-oriented DBMS, in which case there's no impedance mismatch, or you can use it by you can bridge it by using middleware, as we discussed before. Now, object-oriented DBMSs have not been very popular in the industry. So if you look at my previous slide, for example, you're going to see object-relational DBMSs as well. Object-relational DBMSs are relational DBMSs in which you also have some object-oriented extensions. And object-relational DBMSs are very popular in the industry. They're very popular in the industry because they basically combine the best of both worlds. They combine the best of the relational environment with the best of the object-oriented environment. So in object-relational databases, you're going to have user-defined functions, you're going to have user-defined types, you're going to have all kinds of extensions which basically come from an object-oriented environment. Here you can see some examples. So you see we have network DBMSs, right? Here you can see a popular implementation thereof is CA IDMS, which was originally shipped by Computer Associates. You see some other names as well. I would already be very happy if you could remember the first name. For hierarchical DBMSs, here you have the IMS system, shipped by IBM. Relational and object-relational DBMS as well. We have some Oracle, Microsoft implementations, and MySQL, which is also open source. And for object-oriented DBMSs, here you can see two examples thereof. Try to remember the second one, Gemstone, for example. Databases are being more and more opened up for distributed processing in a networked environment, right? So that means that multiple users need to simultaneously be able to access the database. So single user systems are obviously no longer of interest, and we want more and more multi-user systems. Multi-user systems are needed in a distributed environment. So the DBMS should control different things here. So it should control multi-threading and or multi-programming. It would, a thread is like a single execution path within a process. Right? So a process can have different threads which basically share a piece of memory space, and using multi-threading you can allow for multiple users to simultaneously access the underlying database. Again, this also relates to concurrency control. The DBMS should have facilities for concurrency control to allow multiple users to simultaneously access the information using concurrency control facilities. So that is really very important, especially in today's networked distributed environment. We can also classify DBMSs based upon system architecture. You can have a centralized DBMS. That means everything is stored on a central DBMS. So the data is maintained on a centralized server, and all queries that are being issued to the database will be processed on the centralized server. This is the default client-server model. The client-server model, you have a server which is going to take care of everything, and the clients are going to make requests to that server. Okay? In a distributed DBMS, the data is going to be distributed across multiple computers in a network. So think about the cloud. You can have cloud environments in which data is being distributed across different computers, servers, resources in a network. Think about the Apache Cassandra project, Bigtable of Google, and so on. A federated DBMS is basically a layer, a DBMS layer that you put on top of a set of existing data sources. The data sources could be anything. They could be old hierarchical DBMSs, old network DBMSs, maybe some relational DBMSs, maybe some Excel files, maybe some emails and so on. And what a federated DBMS is going to do is going to put a layer on top of that such that it provides a uniform access to all these underlying data sources. So it's going to hide the low-level implementation or storage details of each of these underlying data sources. And a very important example there is the IBM DB2 information integrator. We can also classify DBMSs based upon usage, because you can have different users that have, of course, different data needs and different needs of processing the data. So DBMSs can be optimized towards that usage as well. Imagine that one of the usages is processing many small updates fast. This is what you're going to do on Twitter. If you look at Twitter, people post messages on there continuously, and they continuously perform activities there like retweeting, answering to messages, and so on. So there, the Twitter database needs to make sure that it can process all these small updates in a very fast way. DBMSs can also be used to distribute large amounts of data over a network of servers. This is what Google is going to do. So it's going to distribute large amounts of data over a network of servers to basically perform its search functionality and to make sure it can very quickly answer all the queries that are being issued to it. Or it can be used to process huge amounts of data over a very short time interval. Process those huge amounts of data using very complex operations. Think about very complex nuclear databases or databases which are being adopted to monitor all kinds of physical processes, as you see at the LHC at CERN, for example. Another way of looking at the usage of databases is by making the distinction between OLTP and OLAP. OLTP stands for Online Transaction Processing. That means processing transactions online. This is basically what a supermarket does, right? In a supermarket environment, you have lots of purchases that are being made, right? So you have lots of transactions that are being made, and your DBMS should be perfectly equipped to deal with those in a very efficient, performing way. So here, the OLTP systems should be targeted towards managing that operational data, and the database server must be able to process lots of simple transactions per unit at a time. Very important is that it consists of simple transactions. Simple transaction is a purchase. It's somebody making a purchase in a particular setting, a supermarket setting, or maybe somebody doing a wire transfer in a bank setting. These are what we call simple transactions. So the transactions are initiated in real time, simultaneously, and you have lots of users and applications that are going to simultaneously access the database. So you have short, simple queries, but a high volume. Well, OLTP systems, these are what we call OLTP systems, and your database should also make sure that it can do this, that it can process short, simple queries, inserts, updates, deletes, but with high volume simultaneously. So again, facilities for concurrency control will also be very important here. OLAP stands for Online Analytical Processing, and there we're going to actually do more kind of decision making. So that means that we're going to use the transactional data and analyze it at tactical or strategical level to make decisions. Think about the supermarket example, for example. There you could use OLAP to see what's the average number of sales in a particular shop, or what's the average number of sales of fruits in a particular shop during the winter. So these are more complex operations in which you're basically aggregating underlying transactional data. So here we have large complex queries but with low volume, but the complexity adds an extra dimension from a database perspective because your database should be able to perform those complex queries. Now, if you're working in an OLTP or an OLAP environment, it will be very important for the design of your data model, because in an OLTP environment, the data model will be designed in a different way than in an OLAP environment. In an OLAP environment, for example, we're going to work with star schemes. A star scheme that has a fact table and different dimension tables, whereas in an OLTP environment, we basically are going to work with just a relational implementation, a classical relational implementation in which you're going to have tables connected with primary and foreign key relationships. But remember, this is something that we're going to come back to later on very extensively in this class. Another way of looking at database usage is by looking at XML. XML stands for Extensible Markup Language, and it's a kind of standard that allows you to specify the content of documents, right? So it's specifying the content of documents, not as HTML. HTML is going to focus on the representation of information. XML focuses on the content of information. So in a native XML DBMS, you're going to use the logical intrinsic structure of an XML document, which is very hierarchical in nature. And basically what you're going to do is you're going to map this hierarchical structure to a physical storage structure. This is completely different in an enabled XML database, because what an enabled XML database will do is it will be an existing DBMS, but which has facilities to store semi-structured data like XML data together with structured data in a comprehensive, integrated, and transparent way. So this is another way of looking at database usage, looking at the way it can deal with XML either in a native way or in an enabled way. Here you can see an example of XML, right? Remember, XML, as I said, is a standard which is going to focus on the content. So here you can see an order with different types of meta information, the date it was put, the client, the product, and for each product, of course, the idea, the price, and a short description, right? So you can see this is very hierarchical in nature. So either you can store this in a native way or in an enabled DBMS way. Grid computing is also something that is very important these days, especially when you're doing complex processing. So if you want to do complex processing, grid computing means that you're going to distribute the efforts of the processing across different nodes in a network. So you're going to have many machines that are going to work together on a task, and we need to share those geographically dispersed resources. So we need to share data, we need to share processing power, storage capacity, network capacity. And basically what you're doing here is you're creating one big virtual computer, one big virtual computer which is going to invoke all the different nodes in the network. So it speaks for itself if you're using a database or a DBMS here, that it also needs to be capable of working with those different nodes, and it will, in other words, will have to have grid computing facilities. Mobile applications are also getting more and more important. Think about smartphones, think about tablets and so on. These are very important examples of mobile applications. And they're typically small footprint systems. That means that they have limited processing power, they have limited storage, and also depend upon battery life. So small footprint systems means that they're very simple DBMSs, very simple database applications, which just focus on very simple activities. They need to be always online, right? So if it's not online, then you're in trouble. Imagine that you have a database with phone numbers in your iPhone, and at some point it stops working. Then this is very unhandy. It needs to be always there because you want to be capable of calling anyone at any time you like. It should always be connected to a database. Think about WhatsApp applications, think about Gmail on a smartphone and so on. So you're going to invoke Gmail from your smartphone and make sure that you're always connected to the Gmail database. It can also allow you to store data in the cloud. You can think about a Google Drive and Google Docs, which are stored in the cloud. And if there's network failure, you need to make sure that you can also efficiently cope with that by keeping some data on the device itself, like most recent emails or messages, such that you can keep on working for a short amount of time whilst the network is offline. Basically, you want to keep that as transparent as possible. So even if the network is online, you want to make sure that you can do certain types of functionality on your iPhone such that when the network becomes online again, your iPhone can synchronize and the information is again perfectly updated. Finally, to conclude this chapter, there's also open source DBMSs, and in this course, we're going to work with an open source DBMSs to actually perform the assignment. Few examples are MySQL, PostgreSQL, Twig, and Perst. The most important one maybe in this class is MySQL, because that's the one that we're going to be working with in the example. So this kind of concludes this second chapter. So remember what we did in the second chapter. In the second chapter, we first zoomed into the internal architecture of a DBMS. We spoke about the DDL compiler, data definition language compiler, which is going to compile all the data definitions and store them in the catalog. We spoke about a DMS compiler, DML compiler, data manipulation language compiler. We distinguished between declarative DML, which is going to declare what we want, not how we want it. That was a very sophisticated way of doing it. Versus a procedural DML compiler, which is going to work out procedures to solve your queries and is more focused on the how. It was also a record at a time, remember. We also discussed the key role of a query optimizer. A query optimizer is going to optimize your query and it's going to make sure that it has a good response time there. We discussed the stored data manager, which is basically the interface to the operating system, which is going to directly retrieve all the data, the raw data, or the catalog data, and make sure that the integrity rules are always respected. Then we talked about different database utilities, loading utilities, storing utilities, utilities for transaction management. We also discussed some of the DBMS interfaces. We looked at GUI interfaces, forms-based interfaces, web-based interfaces, natural language interfaces, and so on. In the second part of this chapter, we discussed the classification of DBMSs based upon the data model, hierarchical, codicil or network, relational, object-oriented, object-relational. We also discussed classification based upon simultaneous user access, based upon centralizing the data. We discussed classification based upon usage, and for usage we made a distinction between, for example, OLTP and OLAP. OLTP was for transaction processing. OLAP was for decision making at tactical strategical level. We discussed also based upon small footprint systems. We looked at mobile applications. We looked at grid computing, and we finished the chapter by discussing open source DBMSs. Now we're ready to discuss the next chapter, which will zoom into more detail on the data models.